Kia ora Year 13. This is another video going through some linear programming ideas. This is an old practice task that I haven't seen before, and it's about Melanie, who has had a fitness check and wants to lose weight by either cycling or doing aerobic stepping, right? So don't blame me, I didn't write the context, I don't particularly like it. But anyway, Melanie is choosing between doing stepping and doing cycling. And she's a geek, so she's doing it with linear programming. So you can pause the video and have a read of this. If you're in my class and you're watching this on Sunday night, please go to bed. I don't want you to watch it before class tomorrow, but otherwise, go right ahead. So Melanie has to decide how many hours a week she should spend cycling and how many hours she should spend stepping. So we'll just start off by, as usual, highlighting the key things. Her choice is between cycling and stepping, and she wants to maximize the calories she will burn. So I'm going to go quite quickly through this because I'm assuming if you're watching this, you've watched some of the slower videos. Now, the tricky part of this is to say that when she gets slightly fitter, the constraints are going to change slightly. And in particular, the rate of calorie burning from aerobic stepping is going to change. And you have to tell her what to do now and what to do later on. So moving on to the second page, we're told that she'll spend at least 9 hours cycling each week and at least 2 hours of aerobic stepping. And she can spend no more than 24 hours in a week, that's not in a day, in a week doing exercise. And we can write it like this. So you can see that we've been given that constraint as C plus S. I'd like us to change that straight away to X plus Y. And we'll start by defining the variables. Okay, but there's one last constraint that we haven't looked at, and it's one of these fiddly ones where we're told that she should spend at least 3 times as much time on cycling as she does on aerobic stepping. So we'll do a little table to make sure we don't have that one backwards. Now, we know that she's trying to maximize the calories she burns, and we're told that she expects to burn 800 calories per hour from cycling and 600 per hour from stepping. I'm going to come back to this last part again later on, but the excellence part is this. After 6 weeks, she thinks she'll get much more active with the aerobic stepping. In other words, she'll burn more calories per hour. And we have to say, by what fraction would she have to increase the calorie burning rate so that she could reduce her cycling time and still maximize the amount of calories burnt? So that sounds kind of confusing, but once we actually look at the graph, it's reasonably straightforward. The big idea is about rearranging the objective function equation to look at the gradient and using that to help us figure out the next step. So let's just quickly do all the usual stuff. We're going to start by saying let X be the number of hours per week spent. What's X? Which one is X? Sorry, just trying to remember. X is the first one, so X is cycling. It doesn't matter, right? You'll just end up backwards from me if you do it the other way around. And let Y be the number of hours spent stepping, and that's both per week. Okay, I'll just change pen. What do we have for constraints? Well, I've typed them up on the next page to speed this bit up. Oops, that's my graph. Where are my constraints? Here we are. Okay, so the first one is that the total time spent per week must be 24 hours or less. The next one is the limit on cycling, that she's going to spend at least 9 hours cycling each week and at least 2 hours of aerobic stepping. Now, it would be really good to have some labels on these. So I'm just going to pause my... Okay, so we just need to have a little bit more communication than what I've done in Word here to say what each one is. So this one is the cycling hours, and this one is the stepping hours. Now, this one here is the tricky one. The X is greater than or equal to 3Y. And the way that I did it was to use a little table to check it. So we know that X has got to be bigger than Y, so she has to do lots more cycling than stepping. So I've put in some values to test that out. So if she does 9 hours of cycling, then is she okay with 2 hours of stepping? Yes, she is. Is she okay with 3? Yes. Is she okay with 4? No, because we have to have at least 3 times as much cycling time as stepping time. And if you're in my class, you'll be used to my silly table way of doing it, but it works pretty well, right? So we just set up those numbers, check which cases are okay, and read it back in context. And that will give us that the cycling has to be greater than 3y or equal to it. So we get that constraint. Now just notice that we usually need the positivity constraints, but we don't need them in here because we've got these two here that are stronger constraints than those. Lastly, we've got to have an objective function, and this is what I've called B for calorie burn. So for every hour she spends cycling, she burns 800 calories, and for every hour she spends stepping, she burns 600 calories. So now we're ready to go. We've done the variables, objective function, and constraints. We're going to put it into a graph, and we're going to work out the calorie burn at the vertices. And that's the answer. Where's my graph gone? Here's my graph here. Right, so it's a really simple little problem with no non-integer values to worry about, just those 4 coordinates. So now we put them into a table and we evaluate the calorie burning. And this is what we get. So in here, what we find is that the best combination, I'm not writing that out as a sentence in this video. Obviously, in the internal, you have to do that, right? It's not good enough just to dump it into a table. So the best combination for her to maximize the calorie burn is this one here. You know what? I am going to write that out. So she should spend 22 hours per week cycling and 2 hours per week stepping for a maximum calorie burn of 18,800 calories per week, something like that. So let's have a look now at the second part of the problem. Where's it gone? Okay, it's this bit here. So she's going to get much better at the aerobic stepping. How much does she need to increase the rate on the aerobic stepping so that she's not doing nearly all her time cycling? So at the moment where we're at is she's doing 22 hours of cycling and 2 hours of stepping. And if we look at the graph, we can see what we're trying to do. And then this problem gets way easier. Right, so at the moment we're sitting here, and that's happening because when I take my calorie burn function, which has got some kind of gradient, and I push that out as far as I can go, I get to the maximum point at this vertex. So how could we have it that she is doing less cycling time, more stepping time, and still be maximizing the amount of calories burnt? Well, you can see that that's going to happen. You know you're going to be on the edge of that constraint. And so what we could have happen is if we can get the gradient to match this gradient, then any of those points are going to be just as good as this one here. So to do that, we need to change the calorie burn rate on stepping so that the gradient matches up to this one here. So what we have to figure out is, what is this constraint here? And what's its gradient? Well, you can see from looking, even if you can't figure out which equation it is, that the gradient of this one is -1, right? Because we've gone, what have we gone? From here to here, we've gone out 4, and we've gone down 4. So the gradient's -1. So if you're smart, then you're used to doing the gradient switch around stuff from in the Walker book, you'll know where we're going with this. Instead of having 800 and 600, which is giving me a gradient of -4/3, you're going to end up wanting to have 800 and 800. But let's do a little bit of maths to show where that's come from more slowly. The other cool thing about Desmos is that you can figure out, if you can't see it straight away, which constraint that is by just looking at the color of that line. Right, so that line is red. If you go into your equations in Desmos, you'll see that that is the x plus y line. So let's see if I can manage to move my view window. No, I can't. However, what I am going to do is stay in Desmos and just show you what's going on at the moment. So hopefully this screenshot is still working. I've put a slider in here which is my burn function for calorie burn at the current prices. And you can see that I'm trying to push that objective function out as far as I can. And at the moment, that gives me a unique solution, and it's at 22.2. So if I can tilt that objective function gradient, I'll have all of that red line segment working out fine. So that's come up now, highlighted. I can't write on the screen, but you'll be able to see it in a moment. So let's now go back into OneNote and see what to do next. Probably you've all stopped watching by now. But this is the tricky bit, right? So what we've got, what I've written up here, is that the gradient of the red line segment is -1. And that's happening because it's the trade-off for the total number of hours. So if we start off with our calorie burn equation when we had 800 and 600 respectively, we can rewrite that to make y the subject. The reason I want to do that is because then I can compare the gradient of this one with the gradient of this one, right, which is y is less than or equal to -x plus 24. So m in here is equal to -1. And at the moment, m in here is equal to -4/3. And that's why, going back to the graph up here, I get a unique solution here. So I need to change it to match the gradient. So how am I going to do that? Well, if we change it and give the calorie value from stepping be something we don't know yet, we'll let that be big M. So instead of having my equation say 600y equals -800x plus b, I've changed it to say my. Then I can rearrange by dividing both sides through by m, and this is the equation that I'm sliding out. I'm trying to make this objective function as big as possible. And our goal to get multiple solutions is to have this give me a gradient of 1. So if I have -800 over 800, my gradient will be -1. Okay, so how big an increase is that? Well, I'm going from 600 to 800. So the percentage change is the 200 increase divided by the original amount, which is a 1/3 increase on the current 600 salaries. The last thing that I should do is figure out how much better her calorie burn is going to be if we do this. And this is what it looks like. So again, I'm not doing the write-up for this now because this video is getting really long. But if you go back to your vertices and you now put them into this equation, 800x plus 800y, you'll get out these. And you'll see what we aimed to get, which is that you've now got multiple solutions along here. So anywhere between 18 hours of cycling and 6 hours of stepping, up to 22 hours of cycling and 2 hours of stepping will give you what you want. And it wouldn't make sense in this context to start to go on about non-integer values, because if you go all the way back to the context, in this situation, there's really no reason that Melanie can't do 13 hours and 5 minutes of cycling, right? So in the context, it doesn't make sense to worry about whether we've got integer values or not. So that's about all there is to it. You've got to be very confident for excellence with the idea of matching up the gradient of one of the constraints with the gradient of the objective function. And if you go back to some of the earlier videos, there's some more practice at that idea in those. Thanks for watching. Let me know if you've got any more questions.